Hello my friends of Hatari Labs, my name is Montoya. Please welcome to this tutorial. What we are going to do in this tutorial is the simulation of the seepage of a water reservoir. So what we are going to do is we are going to model how much water will be losing a water reservoir through the flow downstream. Okay, so we are going to do the numerical simulation, okay, and then we are going to do the 3D representation, and as well we are going to determine the amount of water that the water reservoir is losing. Okay, so let's start. Okay, we are going to do a review of the spatial database. Okay, there was a question saying how do we create the input data. The input data is actually created from the utils to determine the watershed and the river network, and this is done with um, utils.hatarilabs.com. Okay, the first thing that you need is a raster them. Okay, and when you have your raster them, you go to this uh, to this uh, to this web app. Okay, and then you enter here, and here you have the watershed delimitation. Okay, and from that you create the folder that is called Hatari Utils. Okay, so in Hatari Util we have the catchment and the river basin. Okay, great. So what else do we have? We have the I'm going to put some transparency here. Okay, so we have the dam envelope, the reservoir envelope, the limit of the model that is actually not the limit of the, because this is a part of the, okay, we are going to work in a local model, a child model. Why we are going to do that? Because we can achieve a more better discretization. Okay, so we can achieve and less amount of cells. Okay, and this is the second part of a tutorial. So there is a tutorial for the regional model. Okay, the tutorial for the regional model is this one. Okay, so this tutorial actually creates a water uh, creates the water table raster. Okay, and then we are going to import this water table raster and apply as a general head boundary conditions on the perimeter of the model. Okay, so for that that is why that here in the reservoir regional foil the only raster is the water table. Okay, great, so that is amazing. What else do we have? No, nothing. Okay, so from that we are going to create our uh, model. So let's start. Like in any other Anaconda prompt, cd documents, cd water reservoir. Okay, and here Jupyter Lab. And for this tutorial, we are going to work on the reservoir file folder. Okay, so all the input, output, model files and BTKs will be created here. Okay, so let's go to scripts. Here you have still the script for the regional, so okay, but now we are going to work with the reservoir. Okay, so here in the reservoir we start a new notebook that is going to be called part 0. Okay, sorry. Okay, so we uh, okay, no, but first of all, what we need is to install the latest version of mf6Voronoi, okay? mf6Voronoi, that is a package that will reach at the time of the video the 20,000 downloads. So, uh, okay, so now we have the latest version of mf6Voronoi, and now we can have the, and this will be reservoir. Okay, well, we can list the templates. Okay, yes. Okay, so first, sorry. Okay, kernel, restart kernel. Okay, yeah. First, we import that. Okay, and then we can list the templates. Okay, so if you are new with the package, so these are the templates we are going to use. The generate Voronoi, the model creation, because we are going to run on a steady state, and the BTK generation. Okay. So here is the copy template of the reservoir. Okay, the prefix will be reservoir. Okay, so the generate Voronoi, the model creation. Okay, great. So now we have the three files: reservoir, generation, model creation, and BTK generation. Okay, now let's go to the mesh. Okay, so first, what do we need for the mesh generation? So we are, in this case, okay, different from the regional model, we are going to use a lot of shape file, well, 4 shape files. Okay, on the regional model, the maximum cell size was 800. Now it has 250 as the maximum cell size, and the multiplier is 1. Okay, so on the dam, we have a cell size of 20, and this is mostly because we are going to represent the slope of the dam, so that is why. Okay, you can work with 10 as well, or you can work maybe with, but yeah, that is also possible. But however, okay, if you want to get a better resolution on the dam itself, okay, you can work with 5 as well. Okay, on the reservoir envelope is 80. Okay, and on the river basin is 80. Okay, so let's see. Okay, according to me, okay, so we have 12,000 cells per layer, so it's not that much. Okay, so we have the problem of short sites. Okay, when you know that you have problem with short site, when you have a Fortran error when you run the model. Okay, so in order to pass this problem, so we are going to uncomment and run these 2 cells. So that is all that you need. Okay, and it says, okay, so you have fixed your mesh. Okay, so and then we do the, okay, so we create the output folder, and then on this output folder we are going to generate our mesh. Okay, and now we open that and plot the mesh. The mesh seems pretty neat. Okay, it's nice. Okay, we have the refinement here on the dam itself, and as well we have the 80. You can play around. I mean, you can decrease that to 1. I mean, but I think that it will be okay. So you are not going to get much more of the simulation by decreasing these to levels of 5 meters, for example. I don't think so. Okay, great. So what else? So we open the shape file. Okay, and here we we create the JSON folder. Oops, sorry. We create the we read the shapefile, we create the properties, and then we save those properties in the JSON. No? So here you go to reservoir files, JSON, and you have the DSP. Okay, great. That is amazing. Okay, so let's go again to reservoir, and now we are going to build the model on the steady state. Okay, so that's it. We need two more lines here, or maybe three. No, two more lines. Okay, those are utilities for the representation and for raster generation. Okay, great. Okay, so we open our JSON file. Okay, so we are going, okay, so now is where it goes tricky. Okay, we have a source elevation. Okay, so this is the elevation, but this is the original elevation. Okay, and then we have the final elevation, that is the surface with the reservoir. Okay, we need these two. Okay, great. So what else? So we need to fix the elevation, the final elevation, okay, that it will be always on top. Okay, or we need that or in this case we need that the original elevation will be always below. Okay, so in the case that the original is higher than the final elevation, okay, here it will be the same. Okay, this is because, okay, so what we are talking about, the original and the final. Okay, so we have done, we here we have this is the original elevation, but there is another topography, that is the topography with the 1100, 1300. Okay, okay, so there is this surface, okay, that it has the reservoir, okay, and as well the slope. Great. So this is the final. Okay, this is the original with the final elevation. Okay, and then we need that this surface will be always on top of the, or like at least the same as the original elevation. So that is what. Okay, now first we need to run this. Sorry. Okay. Mhm. So if you go to the regional model has 10 layers, but the first layer, okay, will be divided into 5. So how do you that? You do that. Okay, you have 14 layers, okay, because the first layer will be, instead of 1, we are going to have 5, but in the end, the overall will be 20, 14. Okay, so in the beginning we have 10 layers, okay, but the first one will be divided into 5, so in the total of that is 14. Okay, so we have the original topography and the final topography, or like M top. Okay, the bottom is 700. Okay, this is the original distribution. okay, the original distribution of layers. You can refer that to the regional model, okay, and this is the, okay, this is division, okay, so the first layer will be divided in five layers, where each has 20% of the total of the first layer thickness. Okay, so we run this. Okay, what is my, okay, if you are new to that, my recommendation is that you follow all the steps of what I am doing, okay, so you get, okay, so if you are really new to mf6Voronoi, my main advice is to follow all the steps of this, okay, okay, to get the sense of what we are going on, okay, and then start to understand, okay, after you have done it and then you got the result, you come back and try to understand all the steps, okay. So that will be my main advice. Okay, great. Okay, great. So this will be in a steady state. This will be the, so they actually they don't it doesn't change. So here we are going to plot that. And as well we are going to do a cross section because we want to see that on the cross section. And as you see here, you have, this is the original first layer, and it will be divided in 5 layers, and this is the dam and this is the reservoir. Okay, amazing. Okay, all the model is saturated by default. Okay, in the initial condition, yeah, we have an initial condition, okay. So because we have the water table, okay, so we have the water table and then we apply that regional water table as the initial condition, okay. Otherwise, you, okay, and this will improve the convergences and the runtime of the model. So, and then we can plot. This is the initial condition. Okay, on the k values, okay, so we are going, the first, since the first layer is divided into 5, okay, this is the k on the original model, this is the k of the first layer, but now it has 5, it's repeated 5 times, kx1, okay, sorry, okay, so now we have the array of k's, and now we have these layers can be convertible. Then we have the intersect object, okay, so we define the intersect object, okay, and then we play around hard, okay. So where in the reservoir envelope, okay, for the first 5 layers, okay, all the cells will be located, will have a k of 1 because it's actually water, so it's, well, we have to provide a k, but it will be a k of 1, okay. So, and this is, okay, on the reservoir envelope for the first 5 cells it will be 5, okay. So for the layers that are upstream, no, downstream of the, downstream of the, for the layers that are downstream of the dam, okay, or in the first 6 layers. Why? Because actually we do okay, actually what we are going to do, and this is something that happens in the, okay, this layer also has a high K, so there is a removal of this portion of soil, and it will be replaced by the dam soil or the compacted soil. Okay, so that is why here we reach it to, and it will have a K of 110 to the minus 8. Okay, even that we can play around with better configuration. I mean, you can even put the impermeable core. That is possible. Okay. Uh, okay, and then we have and then for the layers of the upstream, and this is more abstract, for the layer that are upstream. Okay, so for the layers that are here, okay, for the intersected cells that go from these cells to the bottom to the layer 6, okay, it will have also the K of the dam. Okay, so this is okay. There are some warnings, okay, because some cells are outside the model domain, but those are just warnings. Okay, so here we can define the Ka, the MPF, and then we can do our representation of the cross section. Okay, finally, after all of these abstractions, we have these are the original layers. We have the reservoir with a high K, and then we have the dam with a grade with a value of a low K value. So if you want to have like better resolution here, okay, because the 20 meters of resolution was applied just here, so you have a better resolution here, you can do it. Okay, you can put that in the mesh generation. Okay, that is up to you. So the storage is okay, recharge and evapotranspiration. Okay, the rivers will be well, they, so we have the rivers. Okay, and it will be conceptualized as drains. Okay, those are clipped, and why they are clipped? Because we are going to use the rivers that are not inside the reservoir, because actually those are not rivers anymore. I mean, there is a reservoir. Okay, so we have here the general head boundary condition, and for the general head boundary condition, we are going to use the water table from the regional file, and then there is a shape file that is called regional flow. Let me show you regional flow. Okay, so what is the regional flow? Is a shape file, is a line that is just a little bit inside of the reservoir model limit. Okay, so this is okay. So this line will help to get the water table and apply it to cells that are to the cells that are intersected with this line. Okay, so that is why this line is not in the border, is a little bit inside. Okay, rotate. So we can, okay, but something that you have to know here is that we are going to use bound names. So in the water balance, this will be registered as regional flow. Okay, the flow that goes in and out will be on the regional flow. However, for the cells, okay, that are the cells on the first layer will be considered as well as general head boundary. Okay, and it will have a fixed elevation of 120 to 1220. Okay, and the conductance of 10. Why the conductance of 10? Because it's 10 times the K, and the K is 1. Okay, and on the boundary condition, on the water budget will be um, named as reservoir. Okay, so we generate the general head boundary condition, and then we do the we generate the observation for this cell. Okay, where the regional flow will be, the name of the column will be regional flow, and the reservoir will have a column of the reservoir. Okay, and this will be the dict, and then we can initialize the, and this will be stored in this file. Okay, then we initialize that, and then we can plot the general head boundary. Okay, let's wait. Okay, so we have for these cells, okay, the regional flow in, because now we are plotting the general head on the first layer. Okay, for this cell, the water table intersects the first layer, okay, but just for this and this and this cell. So if we say MF layer 1, okay, we are going to see other cells, okay, but however, on the reservoir, this water reservoir, all the cells are in the first layer, so that is why you are seeing the whole reservoir here. Okay, so here we have the water budget, and then we run the model. Since we have used the water table as the input model, so we hope that we are still, there is a convergence simulation. I think so. So we might increase the amount of iterations, or you can go to the list file. Okay, whatever what I'm talking, and now we are going to see the percent error. Okay, so let's see, reservoir files, model files, LST file. Let's go to the bottom. Oops, there is a discrepancy. Yes, and the discrepancy, where is it? There is more in than out. So I think that is related to the GHB. Okay, so maybe one was too much, so it's okay. Let's see. Okay, okay, I can try without, okay, just setting to 1, and let's see if this decreases. Okay, so now kernel run all cells. Okay, yeah, you know that when the conductance is too, because we are talking here, we are talking about a difference in conductance, or difference in K and conductance of to 1 to 10 to the minus 5. So this brings and convert instability to the matrix resolution, and that will lead to those problems. Okay, let's see. Okay, so now it's looking for the solution. Okay, let's see right now which is the error. uh, mm, Once again, interesting, because the error has increased. Why? Okay, yes. Okay, I don't want to. Okay, yes. Let's let's do that to 10. Okay, I don't know. Okay, restart. There might be a problem here that we have to fix that out. So you have my email, saumontoya@hatarelabs.com. So if you have any problem with that, if you find the solution, yeah, I'm always happy to help. Uh, yep, your okay. I will really value any hint that you have here. Okay, what I might. Okay, so maybe I can increase the amount of iterations. Maybe. Okay, you can play around with that. Okay, still there is a discrepancy here. Okay, so there is the representation of the water. This is the representation of the heads on the third layer, in the fourth layer. Mhm. And now what we are going to do is the representation. We are going to do a nice representation over the. Okay, this is a beautiful representation of the water table, or no, over the heads on the layer 4, that goes from the reservoir, okay, and how they go downwards, okay, and then you see the flow in this direction, but as well you see the flow in on the sides, okay, and that is really interesting to know. Okay, so you want to know, okay, let's go and to see how much water the reservoir is losing. So you go here to this file, the ops CSV, and then you see that the regional flow is bringing net of 880 liters per second doing the conversion, and the reservoir is losing 1 cubic meter per second to the bottom. Okay, great. So that is but we have to mention that here there are some uncomplex issues that we have to overcome. Okay, so finally, let's go here to the reservoir, and let's go here to the creation. You are not going to see that because I have more kernels here. So we are going to open the model files. Okay, so we run the first one, the second one. The VTK folder will be located on the reservoir. Okay, there is only one model. We open that model, and then we generate the geometry, the parameter, the boundary condition, the heads, and the water table, because this is on steady state. Amazing. Let's wait a little bit. If you want to see the mesh, okay, just to the mesh of the reservoir file on output you can see the mesh that the Voronoi has created. Mhm. Beautiful. Okay, so it has created it. Let's open ParaView. It's taking some time. Okay, so it took some time on the GHB. Great. So let's see. So we open that and then we go to documents, we go to the water reservoir, we go to the and then we go to the okay, first the drainage network. Okay, so these are the drainage network. Solid color like this on surface with edges. Okay, now let's open the general head boundary condition. Okay, this is the general head boundary conditions that I would like to have another color. Okay, for example, yeah, and this, well, you have also the reservoir, but this is just the first layer of the reservoir. Yeah, then you can have the water table. This is the water table, for example, like this, the inverse of that. Okay, and then you can have as well the, for example, we can open the water heads. Okay, and there is a procedure because we want to see the isosurface. Okay, you can put surface with edges, for example, but we want to do first we do a threshold. Okay, because we only need the active ones because we are using Newton Raphson. Okay, and then we do cell data to point data. And then we do a ISO volume. This is the procedure. And then we do the contours. These are the contours. Okay, and then we generate the contours. Okay, the first one actually we delete. Okay, no, again we generate 10 contours, then we do apply. So this is the distribution of the potential, the isosurface. Okay, and this is a great resource to see how the to analyze how the water reservoir is affecting the groundwater flow system. Okay, so that will be okay. Many things we have discussed on this tutorial, and we hope that this tutorial will be useful. My recommendation is that you follow all the steps. Just to mention that we are Hatari Labs, and what is Hatari Labs? Hatari Labs is a platform for knowledge sharing in groundwater modeling. So we have a lot of courses in our website of shop.hatarilabs and elearning.hatarilabs.com. Okay, so you can take elearning.hatarilabs.com. So, and by taking our courses, you support our research, and you do what else? We have a pay if you want to still support our research, and then and this you want to give us your moral support as well, you can be one of your Patreons where you have some benefits in the access to the tutorial and for just $5 per month. Okay, so that was all. Hope to see you in coming courses and have a great day. Que viva software libre.